See, I was thinking of recording from EA1, not this moving call galvanometer. But okay, you're saying so, we can record about. So now, what is the moving coil galvanometer? We already know about this, guys. Hello, can you hear me? Right. Now, first of all, let's see the construction as well as the working. So when we talk about the construction, what all parts are required? These are two magnets. Can you see? These are two cylindrical magnets or whatever you want. I think let's name them cylindrical. These are your cylindrical magnets. What is the purpose of using the cylindrical magnets? To create a
Radial magnetic.
radial magnetic field. What is the importance of this radial magnetic field? We'll talk about later. Radial magnetic field. And what else? There is a coil. So let's say everybody is able to see a coil, right? Yes or no, guys? Can you see a coil?
Yes, sir.
And there is two spiral springs.
Yes, sir.
Two spiral springs. What do you mean by spiral springs? Have you seen this springs which are in the shape of a spiral? Okay. So there are two spiral springs, one in the top and one in the bottom. We won't be able to see this thing. First of all, now what is the function of these radial magnetic, cylindrical magnet? It is to create a radial magnetic field. The radial magnetic field looks like this. Can you see? So this is your radial magnetic field. Yes, please draw the diagram along with me. Now everybody is able to understand what exactly radial magnetic field means. Can you see this over here? Radial magnetic field means basically a magnetic field which is directed along the radial line. Can you see this is cylindrical? So basically there will be a cylindrical gap over here. So now suppose this is your cylindrical magnet. Okay. Basically you won't be able to see this particular part. This is the north pole, and similarly there will be a south pole over. And now you understood what is the shape of this magnet and all, right? Right? So this will be your south pole. So can you see? It's something like this, holding like this. Are you getting my point? So this is basically the magnets, and they are like cylindrical. Like, okay, is this clear, guys?
Yes, sir.
Yes.
Now after
Yes,
this,
sir.
what is there inside? What is there inside? Let's see. How exactly is this part? So there is a support. On this support, we have this thing. This is the armature, or basically this is the place about which the whole thing rotates, right? Then the rectangular frame which we had, this, can you see over here the wooden, this thing, the rectangular block which we had over here. This rectangular block looks like this. So can you see a frame, guys? Can you see a rectangular frame over here? Yes or no? Guys,
Yes,
is
sir.
everyone able to see a rectangular frame over here? This is the rectangular loop, rectangular frame on which the whole copper wirings will be placed, right? Okay. And I told you about the two spiral springs. The springs are over here, and one more is over. So, guys, can you see these two spiral springs, C1 and C2? So, what happens basically? Current comes from here and goes through this part up, and from this part it goes here, then here, then here, then here, then here, then here. So basically, can you see this galvanometer, guys? Everyone can see this galvanometer, right? There is this rectangular
Yes, sir.
frame A, B, C, D, on which large number of copper turns are there. So these are your cylindrical magnets, then rectangular frame A, B, C, D, generally made of soft iron core. Okay, generally it's not necessary. So made of soft iron core and large number of turns of copper wire. Why copper wire? Because these capacitors, right? So now basically what will this magnets do? Magnets will provide a radial magnetic field. These radial magnetic field, what will we do? When we'll pass current through this loop. So now can you see over here? Suppose for example, this is the loop. This is how the loop is placed. This is the front view. This is the top view. So let's say initially the area vector is in which direction? Let's say the area vector is in this direction. है Not necessarily the loop is placed like this. This is a cylindrical magnet. It is enclosed completely. It is like a C-shaped structure. So basically, the magnet will be stored till here, right? So can you see when you will be there, having this particular arrangement in which you create a radial magnetic field for any type of area vector, whether it is like this, and suppose if the this thing rotates, when this thing rotates, area vector will be pointing in that direction, right? So for every possible direction, cylindrical magnet is to create a radial magnetic field for so that the magnetic field will always be perpendicular to the brain, and hence maximum constant torque is observed at every time. Is observed at every. Is this clear, guys?
How is the magnetic field always perpendicular?
Because we are, can you see, suppose at this instant if the loop makes like this, so can you see this was the area vector, right? So by creating a radial magnetic field, can you see there will be one magnetic field which will be always perpendicular to this? Yes or no?
Okay.
So that is why. If the loop becomes like this, then the magnetic field will be like this. This will be the magnetic field. This will be the area vector, right? So by creating a magnetic field, a radial magnetic field, we can just we can reduce a constant torque anywhere, everywhere. Okay.
Okay.
Okay. Hello. Is this clear, guys? Now, copper wire used to be a. Now, can you see the two springs C1 and C2? C1 and the C2 are two spiral springs connected at the top and the bottom. And there will be a needle as well. Okay, which will be pointing in the direction of current. It will be also twisting along with it. So this is the construction. What is the principle on which it is working on? Can anyone tell me what is the principle on which it works? Guys, can anyone tell me what is the principle on which it works?
Torque experience.
Whenever a current carrying coil is placed in a uniform magnetic field, it experiences a torque, which is given by, what is the value of this torque? Torque is equal to V into I into A minus sin theta. Here, since you are producing radial magnetic field, this will become 1, right? Theta will be 90 at average. Oh, sorry, sir. Hello, Rishma? This will be the magnetic field, and when it becomes like this is the area vector. This will. Are you getting my point? Krishna, can you see there is always one component which is always perpendicular, right?
Yes.
So
So
now,
can we replace theta with 90?
can we?
Replace theta with 90?
We have to replace theta with 90 over here, no? Can you see 90 degree? In this case, theta will be 90
So the torque will always be
constant,
EI.
bi into na. That's it. Okay.
Okay, sir.
Now let's talk about working. Working, I will not write the whole thing. Working, you people just understand what exactly is the working. See, when you pass current through this conductor, what happens? When we pass current through this ABCD loop, what will happen? This loop will experience torque, है ना? When current passes through ABCD, the loop experiences torque. And what is that torque? The torque will be B into I into N into A. Yes or no? Hello? Yes or no?
Yes, sir.
So torque will be equals to B near here. Theta will be 90 degree as radial magnetic field is produced, right? So this will be the X torque due to the magnetic field, or torque basically because of the current. Now, when the torque starts rotating, when the loop starts rotating because of the torque, because of external torque, the springs also get twisted, right? Yes or no? Hello guys, will the springs also get twisted? Shall I write C1 and C2? It's fine. The springs also get twisted by a certain angle. So what will happen when the springs will get twisted? They will apply a restoring torque. They will apply a restoring torque which is directly proportional to the angle of twist and acts in opposite direction. So suppose if the twist is clockwise, then this restoring torque will be anti-clockwise, right? Yes or no?
Yes, sir.
Yes, sir.
So basically, this restoring torque and that external torque will get balanced at certain angle, right? Initially they will not get balanced, but afterwards they will get balanced after some time, right? Yes or no? So this restoring torque is basically equals to minus of some constant, let's say k into theta. Can you see this particular thing? Torque was directly proportional to minus of theta. When you remove the sign of proportionality, you get a constant multiplied, right? And this is vector wise. Yes or no? So just magnitude wise, if I write, can I write the restoring torque is basically equals to k theta? Yes or no?
Yes, sir.
So if a needle is now connected to the coil, so based on the amount of the current flowing, the reading can be obtained. So now everyone understood the working, right? I'm not reading. Is this clear, guys? So this restoring torque will be there, and this external torque will be there. For a constant reading, this external torque and this reading, this restoring torque will be equal, right? Achha, by the way, C is called as the stiffness constant. C is basically the stiffness constant of spring. Or C, yes, sir. The constant. So is this clear? Guys, is this clear? Have you written till here?
Yes, sir.
Yes, sir.
So when the coil is in equilibrium position for a particular current I, at an angle theta. This theta is basically the twisting angle, okay? So this torque, external torque should be balanced with the restoring torque, and hence we can write VINA should be equals to K multiplied by V. Yes or no? So from this, can you see over here? This theta can be written as V A N K into Y. Yes or no? Yes or no, guys? This
Yes,
thing.
sir.
Now tell me, the magnetic field is because of the magnets which are enclosed inside, right? Will it be changing? Will it be constant or will it be changing? It will be constant, right? Because we have strong magnets inside. Area of the loop we are not changing. Number of turns we are not changing. The constant K we are not changing. So this whole thing which is written in the bracket is basically a constant, and we can say this particular thing that theta is directly proportional to I. More the angle of twist, more will be the current. So can you see direct proportion relationship? So when I remove the constant, I can write it as this constant can be termed as S is a constant
So
called
here
as
theta is maximum angle of twist.
is theta is basically the what? Yeah,
What
for
is
one
theta?
particular current you will get a reading, no? And you will notice the reading only when you know that way that needle will come and stay at one particular position, right?
So that is the maximum angle of
That
twist.
is the angle of equilibrium position. Yeah, maximum angle you can say. Not the maximum angle like this. For example, suppose if the reading, the scale is from here to here, let's say this is your 0, and let's say this is your 5 ampere, but your string, the needle from 0 it came to, let's say, 3 ampere. So I'm not talking about यहाँ से यहाँ तक का angle. I'm not talking about this. No, I'm talking only about this angle, where the spring has come and came to be at rest, right? Equilibrium position, where the needle is came to be in equilibrium. I'm talking about this thing. Okay.
Okay, sir.
So will we have values in a galvanometer,
What values?
like the scale? We
Yeah.
won't get reading,
No,
right?
galvanometer measures also, no? It measures a very small amount of current. That implies, this 3 ampere will be 3 milliampere and 5 milliampere. It measures a very small amount of current. I'm just giving an example of it. Okay.
No, like I'm asking generally, can we measure in a galvanometer?
You can measure. For small currents, you can measure. For big currents, you need to use an ammeter.
Okay, sir.
Now, S is basically called as S is called as sensitivity of a galvanometer. And which sensitivity we are talking about? Current sensitivity. Is this clear? Then what is this S? S is basically equals to bang. BAN. Okay, is this clear, guys? Any doubt? So this is one of the concepts which was just remaining, and that's. So there is one more factor which is called as uh, 1 upon S, which is basically called as reduction factor. It's basically the reciprocal of resistivity. It's called as reduction factor. Sensitivity. Sorry. Clear, guys? अच्छा एक और point you can write. More the sensitivity of galvanometer. Okay. Whenever we say this galvanometer is more sensitive, that implies it will give more deflection for a small value of current. This clear? Done?
Done, sir.
So this was the only thing which was left in this thing, and rest everything we did. Okay. So with this thing, I am done with the magnetic effect of electric current. Let's start with a new chapter called as called as
Yeah.
electromagnetic induction. So first of all, everyone, are you aware of what exactly is electromagnetic induction and all? Huh? Yeah, but before starting with electromagnetic induction, let me discuss something called as magnetic flux. Do you remember this thing, electric flux was there, right? There was electric flux, right?
Yes.
Similarly, there is magnetic flux as well. before understanding electromagnetic induction, first heading which we need to study is basically called as magnetic lux. Okay, denoted by phi m. What is magnetic flux? Just like electric flux, it is defined as the measure of number of magnetic field lines. You remember the same thing, electric field was also there. In place of magnetic field lines, it was electric field lines crossing the surface, the surface normal to it, or perpendicular to the surface. You know? They are crossing the surface there, but they are crossing perpendicular to the surface is called as magnetic. Okay, is this clear, guys? This is called as magnetic flux. This is the definition. It is a scalar quantity. Can be positive, negative, as well as zero. The SI unit is what is the SI unit? SI unit is Weber. SI unit is Weber.
Tesla meter square.
We'll come back to SI unit how exactly it is there, right? Weber or basically Tesla meter square. So always remember 1 Tesla meter square is basically named as 1 Weber. Please remember Weber is the unit of magnetic flux. Weber is not the unit of electric flux. What was the unit of electric flux? Is there anyone who will tell me what is the unit of electric flux? No, there was a question in which I got confused once. Na? Note, Weber is unit of magnetic flux, not electric flux. Okay, is this clear, guys? Weber is the unit of magnetic flux, not electric flux. Because once I got confused, Weber is the unit for both the fluxes, right? I thought like this, Weber is the unit for both the fluxes, which was wrong, and I lost 5 marks in that question. So that's why it's a objective, no? So 4 marks for wrong and 1 mark for negative marking. Although it is very silly, yes or no, but it's a very minute detail which people generally don't, pay attention on, right? What is electric flux? Achha, what is the unit of electric flux?
Newton meter square, Coulomb raised to -1.
Newton per coulomb into meter square. This is your electric field and this is your area. Is this clear? So SI unit, you remember, na? Is this clear? How is it calculated, sir? It is calculated by, how was electric flux calculated? E dot A, if you remember. Yes or no?
Yes.
Similarly,
Yes,
here
sir.
it will be calculated by dot product of B vector and A vector. Is this clear? Suppose it suppose if you have an area like this, and can you see the area vector of this thing will be like this? Will this be the area vector? Yes or no? And if I
Yes, sir.
say if have you understood now? So basically, can everyone see a magnetic field like this, and can everyone see an area vector like this? This is the surface. This has the area A, and if I say the angle between them is, let's say, theta, then magnetic flux will be defined as B dot A. Is this clear? Is this clear,
Yes, sir.
everyone? You can write this thing also as B A cos theta. And what is theta? Theta is the angle between. Okay. You can write one more thing. If you remember, electric flux also was basically magnetic field multiplied by the area which is perpendicular to it, or the component of magnetic field which is perpendicular to the area. So basically the product of the perpendicular ones, right? You can write this as well. Shall I prove this now? Suppose if this is your this was your area vector, and this was your magnetic field vector at an angle theta, then you can do two things. Either you can resolve this area vector into two components. So I can so here I can resolve area vector into two components. One is basically the vector which is perpendicular to B, and one is basically parallel to B. So A parallel and A perpendicular. Okay. What is this A parallel?
A cos theta.
There is something wrong. This is parallel. No? We are taking with area vector, no? नहीं इसको एरिया वेक्टर से ना करो इसको ऐसे करो so if this was the magnetic field and this was the area vector, you see the area vector initially was something like this. Like this, yes or no? So that the area vector was going upwards, right? So here I can, can you see over here? I can do two things. I can resolve this magnetic field into two components. I can say this angle was theta, right? Was this angle theta? So this will be the perpendicular component, which is basically B cos theta, and this will be the B parallel, which is B sin theta. I can write this thing here, B perpendicular the component of area not area vector, okay, the component of area which is perpendicular to perpendicular so can you see basically this thing multiplied by the basically this one. Okay, is this clear guys? Now you understood this formula, b perpendicular. So I cleared it out. What exactly is b perpendicular? B perpendicular is the component of magnetic field which is perpendicular to the area. And what is a perpendicular? A perpendicular will be the area which is a perpendicular will be the area or basically the component of the area which is perpendicular to the so suppose can you see this thing guys? I can divide this area into two components. One area, the component of this area will be perpendicular to this thing, and the second area will be parallel to this, right? Yes or no, guys? Basically, this is the perpendicular area, and this is the parallel area. So basically, b multiplied by, or if you are feeling this as very complicated, even I feel this is complicated. Don't use this. Don't use it. Use this as this is easier, right? Is this clear, guys? So basically, this will be b, this will be a perpendicular, so this multiplied. Okay, guys. Although when we will do applications, then it will be very much clear to you. Okay? Don't use this, guys. Okay? Because this is typical. It is a little bit difficult. But once you do it in applications, it will be easier. Concept-wise, it will be difficult. This will be easier because resolving a vector quantity we know. Resolving a vector quantity is easy. B parallel, B perpendicular, and you multiply. Is this clear?
Yes.
Now we'll see the types. What are the types? First is positive, second is negative, and third is zero. Right? When will the positive flux happen? When the angle between the area vector and the this thing. Positive flux will be when theta is between
0.
90 degree and 0 degree. Then the flux will be positive, right? Basically, if this is the area, this is the magnetic field. So can you see the area vector is like this, and this angle which is found is in between 0 and 90. So whenever angle is between 90 degree, magnetic field lines will be passing through that circle, right? Will be like magnetic field lines are coming out of that circle. When this will happen, then the magnetic flux will be positive. Special case when theta is 0 degree, what will happen? The phi m will become maximum, because cos 0 is basically what? 1 plus 1 over there, right? So the maximum flux will be plus of magnetic field multiplied by. Please note down till here. Guys, positive flux done. Everyone wrote it down. Guys, everyone wrote it down.
Yes.
Don't
Yes,
write this
sir.
dot in here, because if you write dot, you might get confused. It is still dot flux, okay? But we apply the value. Now, when will the flux be negative? The flux will be negative when the lines will be from 90 degree, when the angle will be from theta to 180 degree. Can you see theta 180 degree ke equal? Now, in this case, what will happen? Suppose if this is the area and area vector is like this and magnetic field are going like this. So can you see here in this case the theta will be what? Theta will be what? More than 90 degree, right? So here the magnetic field lines will be going into the surface. Always remember the area vector, we choose it in such a way that it is always coming out. So here in this case, the flux will become negative. Special case is when theta is 180 degree. When theta will be 180 degree, then phi m will become minimum, as cos 90, cos 180 will have its minimum value, which is basically minus 1. Hence the flux will. And in the last case, if E is 0, then Fm is 0. If A is 0, then Fm is 0. If theta is equals to 90 degree, then cos 90 is also 10 of the flux. The flux will be 0, then lines become parallel to the surface and do not penetrate the surface. Are you getting my point, guys? If the lines becomes parallel to the surface, so they will not penetrate the surface, hence no flux. Please write it. Tell me to scroll up and down wherever required.
So could you scroll up?
Yeah. So all these formulas which we have discussed till now will be applied when the surface is plane, right? But if the surface is curved, then what will you do? What will you do if the surface is curved? You choose a small area element. Then, hello people, are you done?
Yes.
Yes, sir.
Yes, sir.
So this is your electric flux. Note all these formulas, all these, all the above formulas will be valid till the time magnetic field is uniform and area is plane. है ना? If any of the two conditions doesn't meet, then none of the formulas are valid which you have written. So what we will do in case of variable magnetic field or curved areas? In case of variable magnetic field or curved areas or both, what we will do, guys? Hello people, can you hear me?
Yes,
Yes,
sir.
sir.
So in case of variable magnetic field or curved area or both, we will use
Small
small,
area.
basically differential small areal element. So basically what will you do? The small flux will be equals to what? P dot D. So for example, suppose if you have a surface like this and if you have a magnetic field like going like this, so basically what will you do in this case? What will you do in this case? You will basically choose a small areal element dA, and can you see the dA vector will be going like this, and this will be theta. So basically the small flux through this area will be equals to what? B dot D, and then basically what will you do after this? The total flux will be basically what? Integration of this and
Integration.
integration of this. So basically do this in case of if this here. Everyone, is this clear?
Yes, sir.
ठीक है, तो वेबर पर
Yes, sir.
मतलब स्क्वायर. अच्छा, एक और since you did remember, I told you, Weber is basically Tesla into meter square. One Weber is basically Tesla into meter square, right? So can you see if I just give this meter square over here, so can you see one Tesla is basically one Weber per meter square? So can you see this is magnetic flux and I am calculating the density, surface density of magnetic field, right? So can you see over here a very important point? Since 1 Weber is basically 1 Tesla into meter square. That implies 1 Tesla can be written as 1 Weber upon 1 meter square. Magnetic field divided by area. So can you see magnetic field? Sorry, magnetic flux. This is your magnetic field. Okay? So can you see over here, guys? Magnetic field intensity can also be termed as flux density. So note at this point, magnetic field intensity or strength is also called as magnetic flux density. Is this clear, guys? This is another name for magnetic field induction. So basically, now this magnetic field intensity strength has three different names, right? Magnetic field intensity or strength, magnetic flux density, and the last one, the third name was basically magnetic induction. Everyone remembers this thing, right? Hello, people, do you remember this? Hello?
Yes, sir.
So these three are the same name. So anything. Is this clear? Shall I give you a question? Shall I give you a question? I'll not give you some easy question. I'll give you some novel question. Uh, question है कि there is a cylindrical copper wire. Guys, everyone is able to see the cylindrical copper wire, right? Of radius how much? The radius is r. Okay. Let us say a current I is passing through the cross-sectional area, or basically the current I is coming. If you see it from here, basically the current looks like coming out of the surface. Okay. Is this clear, guys? Current looks coming out of the surface. Current is coming out and uniformly distributed throughout the area. I want to find out a long copper wire carries a current I ampere. Calculate the magnetic flux per meter. Calculate the magnetic flux per meter of the wire. Let me draw that surface. Yes, guys, are you able to see a rectangular surface? Suppose if this is your cylinder, so basically the rectangular surface is lying like this, okay? Yes or no? So this is your surface S. Now the question is, wire carries current of I ampere. Calculate magnetic flux per meter length of the surface S inside the wire. Chal, please start. Think carefully. Achha, for your hint purpose, I'll give you the magnetic field inside a solid conducting cylinder. If you remember, it was equals to mu naught by 4 pi into twice of I by r square into small r. है ना? किसी को याद नहीं हो तो go to magnetic field, magnetic effect of electric current. See this formula for a solid conducting wire, current carrying wire, solid conducting current carrying wire. This is the magnetic field inside, right? And please remember, this magnetic field depends on the distance from the So does everyone know the direction of this thing? When the current is coming out of the plane uniformly, then can I say this particular thing? Cross sectional area, if I draw, this is the cross sectional area of the wire. The current is coming out, and we know the magnetic field at a point R inside is basically acting in what direction? This will be the direction, right? Will this be the direction of magnetic field inside? The magnitude is this, and this much is clear, right? So can you see over here? This is perpendicular to this thing. Okay. Hello. Hello, guys.
Yes, sir.
Everyone knows that this is perpendicular, right? Now see this thing, guys. The surface S was lying over here. Yes or no? Was the surface S lying over here? So at any point on this surface, will the direction of magnetic field be like this? At any point on the surface S, magnetic field will be perpendicular to the area, not the area vector, है ना? Magnetic field will be perpendicular to the area, or I can say magnetic field will be parallel to the area vector. Yes or no, guys? Yes or no?
Yes, sir.
Okay. So basically, suppose this is the top view, and when I see this cylinder from the top, it will look something like this. If I look the cylinder from top, this is the surface S, that the surface will be like this, and color change. This is now. Yes or no, guys? Will our cylindrical wire look like this? The current is going in this direction, and this will be our surface S, the blue one, right? The angle was this thing. So basically, guys, now what to do? Can you see? As you move away from the center, the magnetic field strength increases, right? So basically, it's the case of variable magnetic field, right? Whenever it is variable magnetic field, now what will you do? At a distance r, there is a hello. At a distance r, there is a small elemental strip of width dr. So at a distance r, the width is dr. The whole distance is capital R, right? The magnetic field at this particular moment will be coming out of the plane. The magnetic field will be coming out of the plane like this. You are seeing from here, okay? Guys, are you able to understand exactly how I perceive the question? Can you see different angles over here? You know, sometimes I see from the front, sometimes I see from the top. So these problems will not be happened, will not be solved until unless you won't be able to imagine the whole thing in front of you. When you will be able to do so, then automatically these problems will become very easy for you to understand. Sir, how exactly are you able to do all these? Are you getting my point, guys? Small things are there. Now, what is the flux through this small strip? The flux through this small strip will be equals to B multiplied by dA. And what will be dA? If I say the length of this thing is how much? If I say the length is this much, L, so it will be B, which is basically mu naught by 4 pi into twice of I by capital R square small r into dA will be L into dr. Yes or no? Will this be the magnetic field? If this,
Magnetic field through the entire wire.
no, magnetic flux through only this strip. This is the magnetic flux through only this strip. This is the magnetic field where the strip was present. This was the area of the strip. And can you see the angle between them is basically 0 degree because the area vector I'll take in the same direction. So
So due to the wire in like at a distance r.
yes,
Small.
this is the magnetic field inside the wire at a distance small r. Okay, so we assume the small strip area this, and hence we are finding out the flux. So the total flux will be mu naught by 4 pi twice of I by r square into L and integration from RDR. Yes. Yes or no? Yes or no?
Yes, sir.
So basically, can you integrate from 0 to R? And can you see what did they are the flux per unit length? So basically, this divided by over there. So the flux per unit length is equals to mu naught by 4 pi twice of I by R square. This will become R square by 2. So 2 will get cancelled, R square to R square will get cancelled, and the final answer is this clear answer. Is this clear? And is this
So what about L?
what about
L.
L either again? They asked the flux per unit length, right?
Okay.
Is this clear? Is this clear?
Yes, sir.
So basically, we are seeing one more formula, which we already discussed. Work done in rotating a current carrying loop in magnetic field in terms of magnetic flux. If you remember, in the last class we discussed work done is basically equals to B into sorry, what was it? It was equal to B into I into N into A into cos theta I minus cos theta F. Yes or no? Guys, do you remember if you were rotating it from theta A to theta F, this was the work done? Yes or no? Was this the work done? Yes or no?
Yes, sir.
So
Yes,
the
sir.
work done will be
Yes, sir.
equals to, can you see? Acha, one more important point, guys. Please remember, take important point. If this flux, suppose in this case, what is happening? There is this one area, right? And suppose if you are trying to find out the flux through a loop, and if the loop has n turns, then automatically this n gets multiplied in the flux, right? So basically, what exactly am I saying? It's like if I say I is outside and this B N A, if I send it inside, so N into B A cos theta I minus N into B A cos theta F. Can I say this? So basically, what will be this thing? Can I write this as I will be equals to NBA, so N into B dot AI, initial area vector, minus N into BAF, final area vector. Can I say it like this? People, love. Can I say it like this? This was initial angle, so initial area vector, and this is the initial area vector and the final area vector, right? So this thing is basically your initial flux, and this thing is your final flux. So what is exactly the formula? The work done is basically I into pi I minus pi. Okay. So now you understood one more formula of the work done.
Yes.
Sometimes people write this thing as work done is equals to minus of I into delta phi as well. Why did they write it as minus of delta phi? Because people know delta means what? Final minus initial. So minus of delta phi is basically initial minus final. So that's why people write it sometimes like this. Okay. Is this clear? Please write it. I'll scroll it up. Okay, guys. Shall I give you a question based on this? Hello. Hello.
Yes, sir.
Shall I give you a question based on this?
Yes, sir.
It's like my ears are paining, for a whole day. It's like headphones is inside my ears, no? Guys, hello, can you hear me? Hello. Hello guys, are you able to hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So question is basically like this. Suppose in this figure, just if I draw question, in figure shown, there is a coil, there is a magnetic field, and there is a coil in which the current is flowing in this direction. Hello. Yes, guys, are you able to hear me?
Yes, sir.
sir.
Sir, are you showing your screen?
And I am showing it now. My connection broke.
Okay.
So this was the figure, and in this figure there is a coil which has a current I in the clockwise direction, and area is A, and number of turns is N. Now my question is, and it is placed in the magnetic field P. So find the work done in required to. Yes. So this is the question. There is this coil, current I, number of turns N, and basically area is A. And now they are asked this particular thing: find the work done to. Find the work done to. Hello guys. Find the work done in rotating this coil by 90 degree, rotating this coil by 180 degree, and pulling the coil out of magnetic field. Yes. We know only this thing. We know that the work done is basically what? Minus of I delta phi, right? Guys, we just learned this, right? Hello?
Yes, sir.
So what is the initial flux? Can anyone tell me? Achha, if the current is going clockwise, what is the direction of area vector? Initial. What is the initial direction of area vector? Into the plane, out of the plane.
Into the plane.
Into the
Basically,
plane.
this is the direction of area vector. So can you see initial direction of area vector and initial direction of magnetic field vector is in the same direction? So B into A into N. cos 0 degree is basically the initial flux. Yes or no? Yes or no, guys? But if we can calculate the final flux, then automatically our work will be done, right? So the first part, when it is rotated by 90 degrees, so the loop becomes something like this. That implies the area vector becomes something like this. Yes or no? Yes or no, guys? Now magnetic field is pointing into the plane. Magnetic field area vector is what is the angle between them? The angle between them becomes 0. So the final angle becomes 90 degree. Hence the final flux becomes 90 degree. Yes, sorry. The final flux becomes 0. So
Yes,
hence,
sir.
in the first case, the work done will be equals to I multiplied by initial flux is B
NBA.
NBA minus 0. So now you got the gist, right? How to do it?
Yes, sir.
चलिए शुरू हो जाओ. Do the second and third part, please. And just give me 2 minutes. I'll just start. Finish these two parts by the time I come.
So what does pulling the coil out mean?
Yes, guys, are you done? Hello, guys, are you done?
Yes, sir.
So what is the answer for the second part?
Just to BINA.
2 BINA. Why 2 BINA? Because when you rotate it by 90 degree, the current in the loop will not be clockwise anymore. It will become anti-clockwise, right? After turning. So basically now the final area vector will be, hello, the final area vector will be coming out of the plane, whereas the magnetic field was still into the plane, right? You didn't change the direction of magnetic field. Are hi Anna.
Yes, sir.
So basically what will you
Yes,
do when
sir.
you calculate the second flux? It will become B into N into A, and this will become cos 180. So this will be minus of BN. So the final is minus BNA, the initial is BNA. So hence the work done will be I into BN. A minus minus. Is this clear, guys? Second work then. Now the third part will be basically you are pulling the magnetic field out of it, right? Pulling the loop out of the magnetic field. So the magnetic field is zero. If the magnetic field is zero, automatically the final flux becomes zero. And can you see the answer will be same as the first part? Yes or no?
Yes, sir.
So I think these questions were easy, right?
You could explain the third part again. I didn't understand.
The third part was given what? In pulling the coil out of the magnetic field. If I want to pull it out of the magnetic field, that implies I want to make magnetic field zero, right? Hello?
Yes, sir.
So that implies the final flux is zero. And the final flux is zero. I'll just put it over here. Okay? Is this clear?
Yes, sir.
I'll give you one more question. है ना थोड़ा सा अच्छा है that the next question will be a little bit good है ना I is over here infinity infinity. Can you see guys this thing what do you call it? Hello. Guys, can you see this thing current I? Okay.
Yes, sir.
And I have a square area. This length is L. This is also L. This is at a distance of R. Okay. What is the area of this thing? L square, है ना? Hello. Now, my question is, let's say initially this नहीं पहले ये करते हैं फिर उसके बाद we'll do the next question. So suppose this is the area. Now the question is find the total flux through the square as shown in the figure. So you need to find the flux through this. Okay. Consider the area vector of this thing into the plane. Why? Because the magnetic field is also into the plane where the square is located, right? So find the total flux through the square loop as shown. Will it be done using normal method B into A cos theta? Hello?
Should we use small element?
Yes, we have to use small element. Tell me the reason why. Why we need to use the small element?
Will there be like a magnetic field by the wire?
Because of the variable magnetic field of the wire. Yes, correct. Now, what will be the element? Guru, what will be the element? Hello. Guru, hello. Ishita, what will be the element over here in this case? Hello, guys. Is my voice clear? Hello. Hello.
Yes, sir.
Yes,
Is my
sir.
voice coming, everyone?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
Yes, Darshana, what will be the small element over here?
So will it be from the wire?
It will be from the wire, but what? What will be the small element? I'm asking. There is what will be the small element in this case?
Small strip of the
Small
wire.
strip. Okay, I have taken a small strip. What all
At a distance.
characteristics? Huh?
At a distance, capital R.
Don't take capital R. Let's take it as small x.
Okay, x with dx.
Badhiya. And what will be the length of this strip?
L
And what will be the width of this strip?
dx. So
Oh,
area will be
perfect.
L
This,
dx.
badhiya. This will be a small element. And now what to do? What is the magnetic field at the place of this small element? What is the magnetic field
B
at the place
dot
of this small?
dA.
Huh?
B dot dA.
B dot dA. So basically, the magnetic flux will be equals to integration of B dot dA. I have taken dA vector in the same direction. So can you see over here? B is how much? B is how much? V naught by 4 pi. What is the magnetic field due to a wire? Arya. What is the magnetic field at a distance x away from a straight wire? Hello, Arya. Can you hear me? Nobody is replying at the moment. Next time, तो मैं फिर ना सबको वो कर. Yes, Abel, can you tell me what will be the magnetic field at a distance x away from the magnetic wire? Hello. Satvik, what is the magnetic field at a distance x away from the wire? Hello guys, are you able to hear me? Hello? Yes, Satvik, tell me.
Yes, sir.
Hello Satvik, yes, tell me please. Satvik has unmuted but he is not saying anything. Yes, Ovia, please tell me. What is the magnetic
Sir,
field?
is it mu by 4 pi 2I by x?
2I by x, correct. This will be the magnetic field due to at a distance x. What is the area? The area will be L dx, and what is the angle? Cos of 0 by integration. Now, so this when you do it, it will be mu naught by 4 pi twice of IL. This will be cos 0 will be 1 dx upon x. Now, what will be the limits? Navina, what will be the limits over here?
Yes, sir. So will it be from
Where will be the first element located?
Isn't it R
X?
to R plus L?
R
Yeah.
plus. So R to R plus. So this will be mu naught by 4 pi twice of I L. What is the integration of 1 by x dx? Trish, what is the integration of 1 by x dx? Hello. Yes, Shirish, I can hear you. What is the integration of 1 by x dx? So ln x, and the limits will be put from R to R plus L. So this will be ln of R plus L minus ln of R, which will be ln of R plus L upon R. Is this clear? So is this the flux clear, everyone?
Yes, sir.
Yes, sir.
Now next question. It's based on this question only. The result we got, which we got in this question. The next question is somewhat like this. There is a current I1 over here, and infinitely long wire. At a distance r, there is a loop of width also r, right? Initially, this loop is having a clockwise current. Initially, has clockwise current I. Okay. Now the loop is rotated by y 180 degree along the axis passing through CD, A, B, C. Okay. So basically, what did you do, guys? You rotated this thing by an angle, 90 degrees. So basically, about this axis, we rotated it. When we will rotate it about this axis, what will it become? Will it become something like this? Yes or no? C and D will
Yes,
be
sir.
still over here, B will come over here, A will come over here. So when this loop is rotated by 180 degree like this, then find the work done in doing so. Which result will you be using, guys? We'll be using this. Okay? And I don't think I need much more explanation in this. I think you people are smart enough to do it this fast. There are some things to be kept into mind, है ना? थोड़ा सा ध्यान रखो. When you will rotate it, what will happen to the direction of current? Will the direction of current be same or will the direction of current be opposite?
Opposite.
Opposite. So basically the direction of area vector will also change and accordingly a minus sign will be put over here, right?
Yes, sir.
Yeah.
Chalo. Do it fast. Chalo, do it. Yes, people. Hello. Sir, my screen is lagging and I can't hear and leave it run back. Okay, no problem.
राखी लेंगे
Yeah. Welcome back to India. Let me just close the gate, guys. My windows is open. That's why. अरे भैया आगे जाओ. Sorry about that. Sorry. Still, you will be able to hear the sound. It will be in the background. So how to do this question? See who you guys.
So I should say the previous time, the previous question we did.
We can just use the result of that. For example, we just calculated the flux. The flux was this. So the flux which we calculated was mu naught by 4 pi into twice of I by what? Well, twice of I into L, and it was R plus L upon R. We know this result, right? Yes or no? We know this, right?
Sir, Ellen.
Ln. There should be ln as well. Ln. So basically, now we know this particular thing. When we rotate it by a version, basically it will be equals to I into initial flux minus the final flux. Yes or no? So can you see in the initial case the area vector and the, can you see over here? This is your AI, and the magnetic field is also into the plane, right? So basically,
Yes,
initially
sir.
the angle between them will be zero, so the same answer will be there. Can you see what is the only difference which I did? I said L and R are equal to each other. If L and R are equal to each other, then the formula will be modified as phi I will be equals to mu naught by. Although please remember, when you get this question, what exactly will you do? You will be doing the same thing. Both the two questions in this question itself. Twice of I ln 2R. Yes or no? Can you see this is the initial flux? Now what will be the final flux? The final flux will be, guys, can you see when you will rotate it, what will happen? The current will be like this now. The current will start flowing in the anti-clockwise direction. That implies the final area vector is pointing out of the plane, and
Outside.
magnetic field is still pointing into the plane, right?
Yes, sir.
So basically, what will be the only difference over here? There will be just a minus sign over here because cos. Acha, can you see over here the distance will be r plus l? So here the distance will be from 2r plus r divided by 2r. So this distance will be 2r plus r divided by 2. Can you see in the previous case it was r plus l divided by r. So can you see when the loop has been rotated, the distance of the closest edge is basically 2r now. Are you getting my point? So a little bit careful about putting these values.
2IR, that R also will become 2R, right?
Which are
Can you go to the formula?
this one?
No, like in the question. 2IR minus mu naught by 4 pi
This
2IR,
will
that R also.
this will become, no, this will be I R only. No, this is twice of I into L. L was R only. No? Are you getting my point? This was L.
Yeah, okay.
This won't be changed. This will remain as it is. So that's why twice of I into R. So this will become 3R by 2, right? Yes or no? So now the work done will be I into mu naught. Acha, I am doing one thing, okay? I into mu naught by 4 pi into twice of IR, then in the bracket it will be ln of 2 minus ln of 3 by 2. Yes or no? Yes or no, guys?
So plus ln of 3, right?
Sorry, minus of this. So that's, है ना? Phi I minus phi f. But can you see phi f was already negative? So minus of minus will become plus. Okay? So I think now it is doable, right? Are hello? ln m plus ln n, ln m into n. So answer will be ln
3.
right? Is this clear, guys? Any doubt? So I think the questions on magnetic flux and this rotation is pretty much clear to you, right?
Sir, can we solve this question without the previous question?
You can
Like
solve
the
it,
formula?
but now what will you do when you will do? You need to apply the formula for individual cases. The same small strip you will calculate. You'll consider the same strip again at a distance. This is the magnetic
But
flux.
we cannot do this problem without this formula, sir.
We can do it better, but you need to repeat the process again. Even when you are solving the same thing, you need to repeat the same process. You need to consider a strip. You need to consider the magnetic flux, small magnetic flux, and then integrate, right?
Okay.
So it's
Okay,
basically
okay.
repeating the same process again.
Okay, sir.
Okay. So with this thing, magnetic flux is over. I think magnetic flux is pretty much clear. Even this result is also clear in which where I am rotating. Okay. Heading Alan, electromagnetic induction. What exactly is electromagnetic induction? Write down heading. My goal is to cover this chapter during your holiday, August holiday. EMI and if possible magnetism and matter. So now electromagnetic induction. Achha, by the way, guys, when did we plan the classes? Was it Monday or was it Tuesday?
So I think it was Thursday, right?
On Thursday.
It was Thursday.
Yes, sir.
So Thursday, what shall be the timing? Because it's now high time to decide it. Shall we take it in between 1 p.m. to 3 p.m. or is this 1:30 to 3:30 time fine? Hello?
So can we have it in the morning?
Morning, I don't have
Yes,
any
sir.
problem. I don't have any problem at all. I wake up at 11 o'clock. In Dubai time, it is 9:30. So I am fine with it. You people, tell me you people. If everyone is fine, then I can take it in the morning. I'm taking it in the
So it's gonna
afternoon
be
so
a
that
2-hour
you
class,
people will
right?
have your lunch and all. By the time you'll be finishing with the lunch and all, then
But
around
10 to 12 should be fine.
10 to 12 should be
Yes,
fine.
sir.
Yeah.
Yeah.
Yes.
Yes, sir.
ठीक. Okay. So I'll just make a note of Thursday 10 to 12. Na?
So what days?
Thursday 10
Okay,
to
fine.
12. Initially, we'll take. Acha, do you want me to take one more day, guys? Because I want to finish your syllabus by November end, before November end. I want to finish your syllabus before November end. Let me just stop the recording.